Hello, everyone. Welcome to the AI Agent Frontier Seminar. I'm Minjin from Virginia Tech. And today we are very fortunate to have Professor Peter Stone from UT Austin join us. So Peter is a Truechart Foundation Chair in Computer Science at UT Austin, where he directs the Learning Agents Research Group, and he's also the Chief Scientist at Sony AI. I've been personally following Peter's group's work for some time, and what's really stood out to me is how it spans the full arc from the deep theory to the real-world deployment. A prime example is the Gran Turismo Sophie project, which I believe many of us have heard about, and it made the cover of Nature. So his team developed an agent that not just beats the world champion driver, but also learned to race with sportsmanship, a rare and powerful validation of these methods. So his research tackles the core challenges of building AI that is both capable and safe, from robotics in the real world to the multi-agent coordination systems. He's a fellow of AAAI, ACM, and IEEE, and also more importantly, he is a leading thinker on how we build the future of AI responsibly. So please join me in giving a warm welcome to Peter Stone. Peter, the floor is yours.
Great, thank you very much, Ming. Thanks for the kind introduction, and thanks all of you for being here. I know there's some people watching live, and others may watch offline. But given it's a relatively small group here live, feel free to interrupt me as we go. I know I'll try to leave time for questions at the end, but I'm also happy to take questions in the middle. As Ming said, I'm coming from University of Texas at Austin, also chief scientist of Sony AI. And my plan for the talk today is, as the title suggests, to go sort of deeply in human-in-the-loop machine learning for robot navigation and manipulation. And I have sort of two threads that I'm going to give some technical details on. But I'm going to start by giving a more broad overview of my research interests and things going on in my lab. So I'm going to spend about 10 or 15 minutes telling you very little about a lot of different things, very sort of surface level. And then later in the talk, I'll try to do deep dives on two different subtopics that are directly related to the title. So first of all, here at UT Austin, it's really exciting times. We were awarded one of the first NSF AI institutes, the Institute for Foundations of Machine Learning. It was just renewed for a second year, 4-year term. That's led by a colleague of mine, Adam Clivens, and we use that to form the machine learning laboratory here on campus. I'm a founding member of a cross-campus collaboration that's even broader than IFML called Good Systems. It's about the sort of ethical AI, or the AI for good on campus. It's inspired and includes faculty from social sciences and public policy and ethics, and as well as computer science and engineering. And it's inspired by the 100-year study on AI that I've been a leader in for many years, that I hope some of you are familiar with. If not, I encourage you to check it out. The third study panel report should be coming out within a year or so, but the first one was in 2016. I'm the founding director of Texas Robotics, and we're going to be hosting the conference on robot learning here on campus next year in 2026. So I hope lots of you will be able to come and see it. It's a beautiful new building. This is what it looked like before we filled it with robots. It was an old gymnasium that they renovated it, 55,000 square feet, full of robots from faculty across campus. And we've also been doing a lot of innovative AI education. I'd be happy to talk about that offline. I'm not going to go in detail, but you can find on my webpage all the materials for an AI literacy course that I created that's geared towards people with no computer science background, to sort of introduce people to not just the latest AI artifacts and programs, but the whole sort of grounded perspective on what AI really is. And we also have, at the other sort of extreme, we have an online master's in artificial intelligence here at UT Austin that has thousands of students in it now, and for $10,000 total, educates people in the details, the technical details of artificial intelligence. So those are the things that I'm very excited about as well. I said that Texas Robotics includes faculty from across campus. We now have 18 core faculty who publish in ICRA, IROS, and RSS. And so, the university has been investing a lot in robotics, and I'll be talking about my own research in this area. But first, I'm going to step back and tell you really what's been driving my research over the course of my career over the past 3 decades or so. And the main research question is the one that's shown here. It's to what degree can autonomous intelligent agents learn in the presence of teammates and or adversaries in real-time dynamic domains? And so within AI, the subfields where we publish are autonomous agents, multi-agent systems, robotics, and machine learning, especially reinforcement learning. And I'll be focusing especially on those topics in today's talk. When I give a one-slide introduction, as Ming said, I do both sort of algorithms and theoretical foundational works, what I call bottom-up research, that builds on the latest technical advances and sort of says how can we advance that. But I also do a lot of use-inspired or more practical research that's inspired by real-world challenge problems. And so when I give a one-slide introduction to my research, it's a lot easier to give a sense of what are those motivating challenge problems. So one of them that I've been involved in for a long time is robot soccer. So RoboCup, or the Robot Soccer World Cup, where our goal is by the year 2050 to have a team of humanoid robots that can beat the best World Cup champions on a real soccer field. That was a video of the old Sony Aibo robots from almost 20 years ago now, playing fully autonomously. When Sony stopped making those robots, we moved to these humanoid robots, the Nows. So this is a clip from the finals of one of the RoboCup competitions a while back. This is about 10 years ago now, where we ended up winning the competition. Ours are the robots with their hands behind their backs. And you have to remember, they're fully autonomous. They're sensing, deciding, and acting. We had to get them to walk, to see the ball. Here you'll see our robot going in on a breakaway. We were playing against the team from the University of Bremen in Germany, which is a perennial powerhouse in this league, but we ended up winning that year. And here you'll see the robot calmly banking the ball off the goalpost and in. The latest, I'm going to actually show you just from a few months ago now. At the most recent RoboCup competition, we had a game, sort of a demonstration game at the end, where people and robots were playing against each other. These are the booster robots. And it was too easy still with the humanoid robots for the people can still go around with the robots. So partway through, I changed teams, and so this is me with the ball, and I'm playing with the robots. And this was not coordinated. I had no idea this was going to happen. But this is now where we're at with humanoid robots, and this wouldn't have been possible just a little bit before. So here you see, I just left the ball for the robot to see what would happen, and it turned around and was able to put the ball into the goal. And so we're really making it, there's really big strides. We set our goal as 2050 to be able to beat the best, team on a real soccer field. So there's still many years to go, but there's a lot of exciting progress going on there. Another domain that it's also a part of RoboCup. RoboCup isn't just soccer. It's also about general purpose service robots. So there's a sub competition called RoboCup at Home. This is a general purpose service robot that we have in my lab. So, if you come, you can often see robots like this one just sort of wandering around in the hallways. But here's what RoboCup at Home looks like. This is a short clip of the kinds of things a robot has to do. So it acts as a party host, or it has to set the table, or it has to put away groceries. So it picks up the milk and puts it on the shelf. This is serving breakfast. So, having to manipulate objects and plan and sense. So this is I think a really exciting event, but for people who are interested in trying to create general purpose service robots. It's very inspiring in a lot of ways. And then, like many, I've been inspired by autonomous driving. We had a car in the DARPA Urban Challenge back in 2007. This is a picture of it. I'm not going to show videos of it. Probably all of you have seen autonomous cars driving now, but back in 2007, we were sort of pushing what was possible. And then we've also thought in my lab, what will the world look like when all the cars on the road are autonomous? Will we still need traffic signals and stop signs, or will we have intersections that look more like this? And so here what's happening is the cars that are yellow, don't have a reservation yet to go through the intersection, so they have to stop. But the ones that are white have called ahead and have a guaranteed path through the intersection that won't collide with the other cars. And so that we did about a decade and a half of research thinking about, how can we expand that to multiple intersections, or if there's a combination of autonomous and human-controlled cars, or if there's pedestrians and cyclists. So there's a long thread of research in my lab on multi-agent systems for autonomous driving. And then one of the, as Ming said in the introduction, my group at Sony has worked on an autonomous race car agent called GT Sophie, and that did appear on the cover of Nature, and back in a few years ago now, 3 years ago or so. And I see it as sort of being in the series of results where an AI agent can do better than the very best human at some task that people really practice at, like chess or Go or poker. So this is, I'll show exactly the task for those of you who aren't familiar. But in the videos I'm going to show, the colored cars are all are an AI agent, GT Sophie, and the white ones are controlled by one of the very best drivers in this task within Gran Turismo. And just like those other successes in chess and Go and things, there was a lot of compute architecture, some top-notch engineering, and then a few algorithmic and methodological insights that put us over the top, and those are covered in the Nature paper. To give a sense of the driving simulator, so this is a top and bottom view of an expert race car driver, Ken Chan, driving a real car in the bottom here, and on the same track with the same car in the simulator in Gran Turismo above. And you see that they track each other incredibly closely. In fact, after a full lap, it was about 1/10 of a second difference in the simulator from in the real world. And so it's modeling, the slipstream, which means, if you're behind another car, there's less air resistance, so you can go faster, tire slip and traction. And this is used by people to train for professional race car driving. And there's people who have put in their 10,000 hours to compete in human competitions. And so in late 2021, we raced against 4 of the best drivers in the world, who are championship drivers, on 3 car track combinations, including one that models the Cirque de la Sarthe, where the famous 24-hour Le Mans happens. And we did it with really end-to-end deep reinforcement learning. This is the standard reinforcement learning diagram, but we started with random behavior, no human demonstrations. There was no human directly in the loop on this. So starting from just random behavior, driving off the track, driving backwards, driving in circles. And 24 hours later, from just pure RL experience, we're able to drive faster than the best human drivers on an empty track. And about a week later, better than in the best human drivers in the competitive scenario. And as Ming said, also then deployed it in the game in a way that allows for sportsmanship and also allows it to be fun. It's not going to be fun for most people to race against one that's better than all people. So we had to sort of make it at the right level for different people. And now if you have a PlayStation and the Gran Turismo game, a PS5 and Gran Turismo, you can race against it. And I think it is one of the biggest commercial deployments of an end-to-end reinforcement learning agent that's out there. Here's just an example of a skill that it learns. Oops, that doesn't work. Let's see. Let's try again. Okay, here we go. So GT Sophie again is the colored cars, so the green one, and the white ones are the human drivers. And here it is trying to just take a line that makes it difficult to pass. It's sort of a defensive line. And so it sort of, it learns successfully to these sort of multi-agent behaviors. There's a lot more details. I have a full hour-long talk on this work that you can find on my webpage. You can read the Nature paper. There's lots of information online. Of course, this is not my own work. It's a work of a very large team at Sony. But that's not the main topic of today's talk. As it was advertised by the title, the main talk is human-in-the-loop learning for machine learning, for robotics. And my lab has been a leader in this area as well. In fact, I think one of the first examples of human-in-the-loop reinforcement learning was the PhD thesis of Brad Knox back in the late, around 2008 or so. I think his thesis was in 2010 or 2012. And this was an example of the sort of first test bed he used was the game of Tetris. So you may be familiar with this, where you're trying to clear rows by dropping blocks. And this video shows random behavior at the start. But what's going on is in the top left corner, you see that a person is either saying good move by flashing green or bad move by flashing red. And this is a task that at the time, state-of-the-art reinforcement learning agents could do fairly well. With hundreds of thousands of games, they could learn expert policies. But here you see, even in the first game, it's starting to do better, much better than random. And then after 3 games, so not thousands or hundreds of thousands of games, with this human feedback, it's able to clear hundreds of rows. So it's not, it's not a perfect policy, but it's a very good policy learned in 2 or 3 episodes rather than in thousands of episodes. And so this was work of Brad Knox, and what we found is that Tamer, using this kind of method where you're taking the human feedback into the reinforcement learning, it could learn much more quickly than autonomous learners, but not quite as well. So after hundreds of thousands of games, the autonomous reinforcement learning agents could do better. So then Brad extended this to a method called Tamer plus RL, which learns both from human feedback and autonomously. It sort of gets the best of both worlds. And then in a collaboration with Garrett Warnell, we extended this to Deep Tamer to be able to use convolutional neural networks to take video input rather than a curated state representation. And I really think Brad, should get credit here, deserves credit for really being the first to introduce the methodology of reinforcement learning from human feedback. RLHF, which, as many of you know, has now become a cornerstone of training large language models. And so this is work that we've been working on, for more than a decade now. We've extended it to also imitation from observation. So there's a thesis from Faraz Tarabi shown here, where he was learning not from a human giving feedback, positive and negative feedback, but rather giving state-only demonstrations where you just see like a YouTube video of an agent acting, and we're able to imitate that either using a model-based method that we call behavior cloning from observation, or a model-free method that's based off of generative adversarial learning. I'm not going to go into details there. And then we've extended that even further, again with Brad, to machine learning from implicit human feedback. So if you're an autonomous car and your passengers look like this, you probably don't need them to tell you explicitly that you're doing a bad job, but you need to get you should be able to just automatically take that as a negative feedback signal. And so with that intuition, we introduced a method or a framework called learning from implicit human feedback, or the LIFE methodology, and an algorithm called empathic that learns to map those implicit facial signals to positive and negative feedback that allows an agent to learn what a person would like in this sort of similar RLHF kind of methodology. So so that's I told you there was going to be a phase of this talk where I tell you almost nothing about lots and lots of different things. And that's what I've done so far. I know it's been a bit of a whirlwind. There's details on all of these things in my papers and in other talks. But what I'm going to do now with the rest of the talk is do some more deep dives that go into sort of human-in-the-loop learning for robotics, first for robot navigation, and then for robot manipulation. And this is all work that's in progress. In fact, this is the wrong citation. This is work from robotics and robotics and autonomous systems letters, RAL, from just last year that I'm going to be presenting, rather than some of the older work. So I'm going to start with this. Let's see if I can get this so that it's actually full screen. Why is it not allowing the slideshow? Okay, there we go. Sorry about that. I just wanted to get it into, okay, slideshow mode. Hopefully this will work smoothly now. Okay, so this is joint work with Louisa Mao, who's an undergrad student actually here at UT Austin, a fantastic undergrad. She's doing work certainly at the level of a top PhD student right now, and she's going to be applying to grad schools this year, along with Garrett Warnell and a colleague who's a researcher at Army Research Lab, and Jyoti Biswas, a colleague of mine, a faculty member here. And this work is like I said, in Robotics and Automation Letters 2025. So, so the human in the loop aspect of this is going to say is that we want to train a model to navigate over off-road terrains that is preference aligned. And what do we mean by preference aligned? It's that a person who's a non-expert can input some information they provide the human in the loop that such, for example, that we really don't want the robot to go through bushes, and it's also bad to go over marble rocks. Grass would be a little better, mulch is better, and then the optimal is to find the pebble sidewalk and the cement sidewalk. And so the person we want to be able to, who's not a robotics expert, we want them to be able to input those preferences, and then for the robot to navigate on a trajectory that's aligned with those preferences, that generalizes to new preferences that weren't available at training time, and also to new terrains that weren't available at training time. So in preference aligned local planning, you have a robot that's looking forwards at the ground that it's about to traverse. It'll have a local, it's whatever it's seeing from its online camera, we translate into a bird's eye view by doing just a transformation so that it can, sort of pretend that it's looking from straight down from the sky at the terrain. And then we want it to generate a cost map, where it's the pixels in the bird's eye view image are labeled with dark for low cost terrain, the kinds of terrain you want the robot to navigate over, and white or light for high cost terrain, the ones that you want the robot to avoid. And there's been work in this space before, but of two different natures, both of which have limitations. So there's a class of work that does semantic segmentation, where we label things like grass and concrete and mulch and pebbles and stuff like that, and then allow a person to tell us what their preference is among those predefined classes. So we could then generalize to new preferences. A person at test time or deployment time can say, well, actually now I think grass is 0.5 and concrete is 0.3 or something like that. You could change the numbers, but you can't generalize to new terrains. You're limited to the predefined segmented classes like grass and concrete that you thought of ahead of time at training time. And then there's another set of work that learns, that does representation learning, learns a continuous representation space and says, from examples, here are some low cost terrains and here are some high cost terrains, and then learns a representation that puts the low cost terrains near each other in representation space and the high cost near each other, which is great for generalizing to new terrains that you didn't see at training time. But now you can't take, it's sort of burnt in which ones are low cost and which ones are high cost. It's not generalizable to new preference orderings. You can't sort of flip and say, now I want you to walk over grass instead of concrete. So our problem formulation, our goal was to be able to get the best of both of those worlds, to basically take a human's internal cost function, H, which is obviously not accessible to us, it's in their brain, and have some way of them communicating in a human-friendly way, some information that indicates what their internal cost function is. And then we want to learn a function R that, given an input image, will map the input image to a cost map, the one that's dark for low cost and high for high cost. And we succeed, we say that R is consistent with H if the cost of the optimal path planned on R, with that cost map, with the resulting cost map, evaluated with respect to the human internal cost map, equals the cost of the optimal path planned on H, as if you had like an Oracle perfect knowledge of the human's internal cost map function. So we're basically trying to see, can we capture what the person wants at test time? And so the way we would do this is we create an interface where a person can just give some examples of more preferred terrain and less preferred terrain at deployment time. So I'd say, I prefer this lighter, colored terrain over this darker colored terrain in an image. I'll show you an interface for that later. And then we use that to sort of infer an approximation of their true internal cost map function, and then take the current image that the robot can see, convert it to a bird's eye view, and then use our function R, which we're going to learn, to generate a cost map and then see where the robot plans. And so the sort of high level schematic view of our approach is that we take a preference context, which is just saying like this, that the person prefers this image to this image, and it really literally just takes three examples. So can click on a couple of pairs and say the ones on the left are preferable to the ones on the right. And then we're going to train, we learn from that a preference context encoder, and also an encoder of the bird's eye view image, and then decode that into an output cost map. And so like some training examples, these are some qualitative training examples where a person gives this preference context, it's paired with this bird's eye image, and here's the correct cost map, right? So it's saying, here are the low cost regions because the person has indicated that they like the concrete compared to compared to the what's up in this top left corner, and they've said the grass is bad. So here's one row here is one training example, and then here's two training examples that show that the output is conditioned on the context, right? So it's the same input image, but if a person gives different contexts, sort of flips the context, then you get a different cost map. And so we obviously have to give some training examples that establish the relationship between the preference context and the bird's eye view image. So what we want in the end from our trained system is that it'll have realistic priors. So that means it'll default to realistic preferences if the person doesn't give any context information. But if the person does give context information, it will follow the person's preferences, even when they're not consistent with the prior realistic preferences. And then we also want this to work on unseen terrains, so terrains that were not seen in the training data and preference contexts that were not seen in the training data. And so the experimental setup that we use is we're going to ask the questions: how well does the planned path adhere to the operator preferences and 4 conditions when we have seen context or preferences that are similar to the ones that were seen at training time on terrains that were seen during training time or part of the training set, but then also when the terrain was unseen, when the context was unseen, or when both were unseen. And I'll show you examples of these as we go. And we evaluate both in simulation and on real robots. And so with these 4 different types of experiments will cover the realistic priors, because if we're if the context doesn't match the terrain, then you have to resort to realistic priors. So that's what these 2 constitute. And then if your context does match the terrain, then you should adhere to the context. So that's what the number 1 and 4 will test. And then we have 2 conditions where the test terrain does not look at all like the training terrain. And so here's what the interface looks like in the end. And I'll show you again. I'll show you a little bit more about how we do the training. But here, a person can choose a patch, and basically, sort of a little square patch. There's one placed and there's another, and then say which one is preferred over the. I think the default here is that the first one is preferred over the second one. So the person is just giving 3 pairs where they prefer the first over the second, and then gives a start position and an end position. And the robot should navigate according to the preferences. So in this case, the person put preferred terrains are the blue ones and non-preferred terrains are the red. And so now the robot is planning a path. And I believe within a little bit of time before the end of this simulator, before the end of this time, it will show a path that stays on the green, on the blue, right? And there it goes. So it didn't take the shortest path. It instead took a path that aligns with the operator preferences. And by the way, this is an example of that was an example of unseen terrain, because all the terrains we showed at training time were grass and concrete. And then this was sort of like a mining region where there's blue roads and red terrain. So it could only be learning from that context. So how do we learn? Well, a lot of this is sort of dependent on the training examples that are given. So we give 3 different types of training data. We first give, we allow a person to give realistic preferences that are, sort of what we would expect to be the prior preferences. So, a bunch of different terrains where a person says, I prefer this to that. And, here's like an example of 3 different preferences shown on the left here. And then we turn that into a total order and generate a bunch of examples that take 3 three pairs, a bird's eye view image, and generates a correct cost map. And so some examples here on the left of a person saying that they prefer the brick over the light brick over the dark brick. They prefer the concrete over grass, and what the input image is, and then the correct cost map. So that's sort of what you would expect would happen most of the time. But then a lot of the key comes from and just this shows that that if we don't give any preferences, the robot will plan a path to avoid grass or avoid dirt. So it's gives adheres to these realistic preferences. But then a lot of the magic here comes in from generating training data sets that then allow us to generalize to the other types of properties. So first of all, we shuffle the realistic preferences and then create sort of different orderings, generate examples with those different orderings and the same images, and then the resulting correct cost maps, and train the agent to learn cost maps that are not consistent with the realistic preferences, but are instead consistent with these shuffled preferences. So here's some example training data of that type. And so in that case, if you compare the, let's jumpy a little bit here, the top and the bottom image, you see the preferences on here are the realistic ones, and the robot plans a path consistent with them. But here we show completely different preferences, and the robot plans a path to now go over the grass and the dirt because the person is signaling that those are preferred paths. And same here, you can induce the robot to go over the grass and the trees if you show preferences that prefer that. And then finally, for unseen terrain, we do a synthetic augmentation in simulation to create patches that look entirely different than anything that was shown in the training set, and again the correct cost maps. And so now we can show training examples that are completely different than anything shown at that the person labeled, and show what the cost maps would look like in that case. And so now we can look at a new terrain, something that's completely different than anything shown at training time. The person can generate patches, and again, can very well control where the robot goes by changing the preferences that they give on these unseen contexts and unseen bird's eye view images. The paper has quantitative results as well. I think these are less, these are tables of numbers, but we basically look at, the percentage of time the robot stays in low cost, medium cost, and high cost terrains compared to other methods, and also with ablations concerned based on which subsets of the data do we train it on. I'll let you look at that in the paper if you're interested, rather than walking through these numbers. But they show that really the whole training pipeline, the data set methodology, and also the training architecture was needed to get this sort of novel result. And so, that's sort of the first deep dive. This is the work, again, of Louis Zamao. We have some ongoing work here where people don't just give binary preferences, but could give sort of weighted preferences and say that I like one terrain a lot more than another terrain. This is, and so this is still, preference aligned terrain navigation is work that we've been continuing on. So that's the first deep dive, human in the loop learning for robot navigation. So this is, and the loop, human in the loop here is both at the training time, but especially at deployment time. I'm now going to shift gears and talk about human in the loop learning for robot manipulation. And this is the PhD thesis work of a recent graduate from my lab, Yifeng Zhu, who is co-advised with my colleague UK Zhu, an associate professor in our department, and also an undergrad, Arisre Lim, who's been doing a lot of work with us. And this is vision-based manipulation from single human videos with open world object graphs. So the idea here is that we're, now we're talking about manipulation, and it acknowledges that robots operate in a low data regime. So you can't get tons and tons of data in the real world. It's too expensive. It's too varied. There's and complex. And so a lot of people have been taken this approach of learning from human data, where a person will do demonstrations for the robot and then use that as a rich source of data that a robot should imitate. So imitation learning plus demonstrations. But in most cases, you have to use teleoperation or remote control devices that can be physically demanding to operate and require high proficiency. and a lot of practice. So our goal in this work is to learn from human video data, something you could get just from like YouTube videos, or maybe just from watching a person doing something themselves. It's easy to collect and also readily available, and it with the idea that it captures human sensory motor knowledge of contact-rich manipulations, and that we can abstract this into information that will be usable by the robots as well. And so there is work in this space that others have looked at, which I'm citing here, where you can pre-train a robot from video to imitate, but most of it requires additional robot demonstrations in your testing domain. You can't just you're going to need to show the robot exactly what you want it to do. Results in a pretty lossy compression. The idea that we're going to use in this paper is that we're going to take a single video of a skill, so not lots and lots of videos of a skill, but a single video of a particular skill, and extract as much information as we can from that one video, basically making that video define the skill. And then if we want to teach a different skill, we take one video of that second skill, and we want to maximally use each video. I'll show you what I mean by that as I go ahead. And it doesn't require any additional robot demonstrations at test time. It just takes the single demonstration at training time. And so this is we see this as a way to scale up skill learning. Like I said, there is a bunch of related work. There's some work on one-shot imitation learning that requires meta-training or additional simulation at test time. There is the video pre-training that I already talked about that needs additional robot data, and also visual imitation from single video demonstrations, but usually requires known objects that were seen at the demonstration time, and often requires like a fixed camera and fixed background so that nothing changes between the demonstrations and the testing. And so our goal, right. So our goal instead is to take a single human demonstration, an actionless video. So by which I mean we don't know what we don't know what impulses were sent to a person's limbs, and or we don't have a robot demonstrating it that's exactly the same, and we know what actions that were taken. And we want a generalizable policy, and we call this open world imitation from observation. And the main insight is that what we're going to abstract from that video is the trajectory, an abstract or lifted version of the trajectory that the objects move through, and that when we're trying to imitate the skill, we want to move objects along trajectories that are similar to the ones shown in the video demonstration, and so that it will generalize to different object layouts. There'll be no predefined number of subgoals, and so like I say, we call this open world from imitation. And the key is going to be an object-centric representation that was something that UK in his past work had introduced, which we'll use to track the object motion in the video, and then at test time map where the objects are in the current world to where they were at training time. And we're going to do automatic segmentation of the video demonstration into keyframes so that we can handle tasks that have arbitrary numbers of steps in them. So I'll give you the details of how this works, but we call our system Orion for open world video imitation. Like I said, it takes the single video imitation as input, and it enables the robot to imitate from this single human demonstration in diverse test environments, which I mean it'll have different spatial layouts, visual backgrounds, camera angles, even new object instances. So that it's a systematic generalization. So some technical detail on how this works. First of all, it leverages a lot of pre-existing vision foundation models. And the pipeline is that it first segments the demonstration in three parts to build out an object-centric representation. So first it will localize the object of interest and find the trajectories that they move through using a visual object segmentation package. It uses a track any point to actually follow the trajectory that the objects move through in the demonstration, and then hand tracking so that we can isolate where the hand is in the video. And then it lifts this into an open world object graph, which basically identifies the relationships between the hand and the objects throughout the video, and represents each keyframes in this sort of manipulation plan. So it represents things like, first, nothing is in contact with anything, then the hand is touching the plant, but the plant is not touching the llama, then the plant is touching the llama and the hand is touching the plant, and then the hand moves away. And this leads us to, we can at test time, we'll generalize to the same task under different conditions. Okay, so a little more detail on how this works. First of all, it's not magic. There are some assumptions. There's some, in this work, I'm going to assume that there's an RGBD video, so depth included, taken with a stationary camera, and that the object interaction is always single-handed, and that it contains a manipulation sequence where the contact relations change among the relevant task, the task-relevant objects and the hand. And there is an assumption that there's a verbal or language-based annotation that gives you the task-relevant object names. So I'll show you what that means on the next slide. So for example, here's an RGBD video of sequence of frames, and a person will give the text description that the things that matter in this demonstration are the small red block and the boat body. And then from that, the method is able to segment out the boat and the small red block using the VLM, identify the keyframes and the key point trajectories that those objects move through during the video, and then outputs this open world object graph that characterizes the sequence of contact relationships among the objects. So here's even one more level of detail where we have that input of the RGBD video and the text description. This is what I showed you on the previous slide, where it gets the object graph, and then to do this, we're basically tracking the key points, reconstructing the hand from the images, segmenting out the objects, back projecting them into 3D space, into point clouds, tracking the objects and where they move through hands or through the video, and then abstracting this into the different nodes for the hand, for the objects, and for the points that are tracked in the video, and abstracting those into the contact relations, a graph that shows which are in no contact or in contact with one another or have a part of or belonging relationship as the robot moves through, as the demonstration proceeds. And then when we want to use this, we can generate actions in a new scene. So here's a new scene with the boat and a red block that's where they have a different background and a different starting position. We have the manipulation plan from the demonstration video, and then we registered those together by localizing the task relevant objects in our current image, finding where they were in the previous image, and now warping the trajectory. So rather than taking it had a start position and an end position and a series of object relationships as shown here, and we remap that to the current scenario. So now it's going to say, well, here's where the red block starts, here's where it needs to end. So here's a similarly looking trajectory that'll apply to the current scene, and then we can optimize this action sequence to find how the gripper should move so that the object follows this new trajectory that's similar but different because of the different starting and end conditions from the demonstration video. So here's the system in action. I'll speed it up a little bit. So in the bottom left is the demonstration video, and then in the middle is the imitation. And you can see that even though it's different from the background is different, the starting conditions are different than the imitation video. We can have a different spatial layouts. All of these are executed from that single demonstration of the person just picking up the succulent. Here's in the top left is a more complex video demonstration. So here, I'll move that back again. It was a two-step one. So yes. So look here, a person's picking up one block, putting it in, a second block, putting it in. And so now here the robot's imitating that with different backgrounds, different starting conditions, picking up both blocks and putting them in the boat. And it generalizes to extreme lighting conditions because the VLMs are able to do that. It's able to find the objects, no problem. And it'll even generalize to new objects. So we just said you care about the mug and the coaster. So if the mug was black and the coaster looked different, it doesn't matter. In the new image, the robot is still finding the mug and the coaster. And so even with different mugs and different, I guess in this case the coaster is the same, but with different mugs, it's able to still imitate that single demonstration. In terms of evaluation, we do this on 7 different layouts. A mug on coaster, chip on plate. You can see them all here. They're different levels of complexity. The word descriptions that are input to allow the system to know what to segment out or what to pay attention to are shown here. So just short phrases. In some cases, it's a bunch of things like the mug, the square mat, the plate, the can, and the cream cheese box. So there's a lot that mattered in this case. And then we do policy evaluation. It's not perfect. So we're not, I showed you some successful cases. It doesn't work all the time. We have about a 60% success rate in most of the cases. In one of the cases, a 90% success rate. But most of the errors are not from the figuring out what to do, but rather misgrasping. Our grasping isn't perfect, or mistracking the vision language models, which are pre-trained and not a part of our, not something that we create, do a little bit of mistracking, or there's some unsatisfied context. So there's room for improvement here, but it generalizes beyond what other people have done in the past to be able to take this single video demonstration and work in a very general set of conditions. Of course, there is still future work here. There's right now we're using RGBD videos. We have actually now generalized this to use just RGB. It doesn't require the depth, which allows really using YouTube videos that exist out there and not having to have pre-collected, specifically collected data. Work that I'm not involved in, but that UK is leading is taking this to a humanoid robot with more complex manipulators. They have a system called Okami, which was an oral at Coral last year. And then also trying to move to more dynamic and forceful manipulations as opposed to these quasi-static tasks. So being able to work with deformable objects and things like that, this method won't apply directly to. But that's sort of that's the second deep dive. That's our vision-based manipulation from single human video with open world object graphs. And so, this is an example of human in the loop learning for robot manipulation. And of course, the human in the loop here is giving those demonstrations. So that's mainly what I wanted to present to you. Again, I did a lot of high level and introduction to the lab, but then did these 2 deep dives: human in the loop learning for robot navigation, where I talked about the preference, test time preferences that can be given just by these 3 pairwise preferences in the new terrain, and the robot is able to follow those preferences for navigation. And then robot manipulation, where a single video demonstration is able to move to be imitated in a wide variety of backgrounds. And so with that, I'll be happy to stop and take any questions you might have.
All right, great. Thanks, Peter, for this fantastic and insightful talk. And let's open up the floor for questions. So for folks here, please feel free to use your raise the hand button, and I will call upon you, or you could put it in the chat. I'd be happy to read it for you.
Hey, sir, may I ask a question? Sir, I didn't see the raising the hand button.
Go ahead.
Okay, yes, thanks. Hi, Peter. Very nice talk. And actually, this is a very interesting topic to me, like human in the loop machine learning for robot control. And my question is that, so basically there are like a variety of different types of human data that we could exploit, like the preferences or human demonstrations. Or maybe some kind of human gestures if you have if you're interacting in the 3D world. So my question is, what kind of data do you think? What kind of humans data do you think is currently underrated that we could kind of exploit more? Or
yeah, that's a fantastic question. So actually, I sometimes give a version of this talk where instead of talking about the preference aware off-road terrain, the pacer work that was off-road terrain navigation, I talk about joint work that I've done with Shui-Su Zhao. It's actually mistakenly left that here in the bottom, called adaptive planner parameter learning, or APPLE. And in that work, we look at three different types of human data. We have demonstrations, which is sort of what I talked about in this case. We talk about also interventions, where a person can not give a full demonstration, but just watch the robot operating using a default behavior, and then jump in when the robot does something wrong and show, here's what I'd rather you do in that scenario. Both of those require a person to have expertise at remote controlling the robot, either for the full task or for just part of the task. Then there's work that's more like Tamer, where it's evaluative feedback, where a person is just saying good move or bad move. And in that case, a person doesn't have to be able to do the task at all. You could use that like to, if I don't know how to fly a helicopter, I could still say that's a good helicopter flight or a bad helicopter flight. And so that's the type of data that we're using in the PACER work, where it's a person is just giving preferences. So I think there's sort of four types of data. There's the full demonstrations, there's interventions, there's evaluative feedback, which could be explicit or implicit. It could be, good move or bad move, or it could be from the facial expressions. And then there's preference data that gives pairwise preferences, like we used in the PACER work. And I think what we really want, and this is what we showed in the work with Tresu on Apple, which we did for robot navigation through very tight terrains, we can put those together in a single agent, so that what you'd really like is an agent that has a very good default behavior in the background, and then as a person, a non-expert, gives any one of those four data modalities, the robot's able to leverage it or use it to improve its performance. And I think that's that would be more like once the robot comes out of the factory and is now in your home, you want these natural user interfaces to be able to be leveraged. So it's a great question. I think all of those different data sources are what we want to be able to enable the robot to be able to take. And we have examples of all of those in my research.
Great,
Yeah,
thank
thanks,
you.
Peter. Yeah, thanks for sharing this very interesting perspectives. Yes, indeed, I think just a follow up on this point, there is a very diverse set of human feedbacks. So when it comes to practice, we often need to find a trade-off between the simplicity of the feedback and how well it actually could convey the human's preference. So how do you actually kind of navigate this trade-off when it comes to asking for the right feedback?
Yeah, I mean, my view is that we want this to be human driven. That if a person, that we should be the agent should be able to accept whatever human feedback the human is willing to or capable of giving. So, if a person is able to, say we take a general purpose service robot, put it in your home, and the robot navigates in the wrong way, it goes through the kitchen when you wanted it to go through the living room. We want to enable the robot or the person to just be able to step in and do any one of those, not the robot saying, please demonstrate, or the robot saying, please give me evaluative feedback. We want the person just to do it, to jump in and either give a demonstration or to, here's how I want you to navigate, to actually teleop the robot, to say, I didn't like what you did. Here's what you should do anyways. A fully capable robot should be able to accept any of those modalities and make it be, sort of driven from the human, which type of feedback is given.
Mm-hmm. Yeah, that's very interesting. Thanks for sharing. So I see some questions from the audience. So let's first go to Nathan Rooney. I see your hands raised, so please go ahead.
Yeah, hi. Sorry, this is Srinivas. Hi, Peter. I'm in Austin myself.
Hi.
So this is when you're demonstrating the preferences, for different kinds of terrain, right? And so it's sort of it really resonated with me because with my front yard and my backyard and my lawn, often I have to sort of think of these preferences, and it gets sometimes a little more specific than just the visual appearance of them. So it might be that for example, if it's newly planted grass, then I don't want the robot or anyone to go over it. Or on the other hand, let's say the ground is frozen. And I might want somebody to go over the grass, especially if it's something on wheels, rather than trying to navigate over terrain.
Yeah.
And I was wondering, or let's say, this being Texas and some of the grass is not green anymore, it's brown. So I'm wondering if, and this is just me thinking aloud, if there's a way of giving some of these preferences in a sort of, expressed in natural language to an LLM, and then seeing if it's able to figure out what the human preference function might be.
Yeah, very good. So that's a fantastic question. And in fact, let me let's see. I can go back to, I can illustrate in a slide here. So in other work, the work I didn't talk about today, the PhD thesis of Haresh Karnan, he basically laid the groundwork for this. So he's, this is precursor work to Pacer. But he took a representation learning approach where what we do is when the robot, so in this video, you see like, the robot is using its camera to look ahead to some terrain. But in practice, what happens is the robot sees this terrain where it is now, and then it takes a step closer and it sees the terrain from a different angle. And then it takes a step closer and it sees the terrain from a different angle. And then eventually it's on top of the terrain and it actually feels the effect of its terrain on its motors, its actuators. And so what Haresh did is he took a contrastive representation learning approach to learn to register what the robot is seeing to what it would feel like when it's walking over it, so that the robot could then map in representation space terrains that feel a particular way to what they look like right now, so that you could so it could learn not just that which grounds it wants to walk over based on what they look like, but also based on what they feel like. So that if it looks the same but it's frozen, then that'll move to a different place in representation space. Or if there's leaf color, there's fallen leaves, and some of the leaves are on concrete and some of them are on mulch, that's going to feel very different when the robot walks over them. And so you were suggesting doing it with an LLM. What Haresh did was learning using contrastive learning and representation learning to try to map not only the robot's vision, but also its proprioception to handle exactly the same problem that you're considering, or that you brought up. But I think you're right. You could possibly, and we haven't done this, but it would be a nice direction for future work then to try to map that learned representation to language, and so that a person could say stay on hard solid ground, and that could be mapped to the place in the learned representation space, or I want you to
I like that.
Yeah, it's a good idea. But so if you want to look at what the representation learning aspect of this, look back at some of the papers of and the PhD thesis of Haresh Karnan, which came, he collaborated also with us and the same co-authors in Louisa prior to this work.
Haresh Karnan. Okay, I'll look it up. Thank you.
Sure. Yeah, and if you or anybody has trouble finding references, any that I mentioned in this talk, feel free to email me. I can point you to the paper on my webpage that's appropriate.
All right, great. So we have two more people in the chat, Li He and Stephen Wen. So please just ask your questions, and Peter can address them together before we end this seminar.
Okay, hello, could you hear me?
Yes.
Oh, hello, Professor Still. I have a more general question. And recently, pre-trained video language action model, VLAs, are very popular. Do you think, are they able to solve the problems that you mentioned tonight, human in the loop, navigation or manipulation or something? And what is your perspective over these new paradigms, new models? Thanks.
Yeah, great question. You want me to get both questions first, or should I answer that?
It's fine either way. So
okay, I'll answer that first. So
yeah.
So I think it's very interesting what's going on with vision language action models. I think it's an open question as to how much you can do from where you use a VLA as a policy, which is essentially learning from pixels to torques. Personally, I think that's a scientifically interesting question. If I have to deploy a robot in a commercial setting, or where I care if it's going to work or not, right now I would lean much more heavily towards still using a lot of the classical robotics algorithms that we know work very well based on control theory, based on model predictive control, and then use the VLAs or foundation models of some kind to inject some high level common sense knowledge But when it comes to actually generating the actions, I think we're still at a place where the classical control theory is going to be much more reliable and much better. I commend people who are giving it a shot to see if they can use the foundation models as the actual robot policies. But I much prefer not keeping the models that we know work and not throwing out the baby with the bathwater, but rather figuring out a way to use the foundation models for what they're good for, which is absolutely for things like mapping to language, for common sense knowledge, things like that, and continuing to use the tried and true methods from robotics based on known models for the low level control. That's my bias. I'll be very interested to see if VLAs are able to replace all of control theory. That's not where I'm placing my bet, but the jury is still out.
I see. Thanks. Thank you so much.
All right, cool. So Steve, do you want to go ahead and ask a quick question?
Yep. Hi, Professor. Thank you so much for the amazing talk. I just have a quick question about the first paper on navigation. So what if you have to take the unpreferred option to get to the preferred one? So for example, like how does the robot navigate through the terrains with alternating patterns when it has to step onto like unpreferred pattern, like to get to the other side? For example, like when from like grass to concrete and then from concrete to grass again.
Yeah, that's a great question. So this is an example actually that ties into the previous question nicely. Is I didn't talk about at all how you go from the cost map to the optimal plan. And for that we just use A-star planning. We use path and sort of regular existing path planning methods that take a cost map and find the optimal path. And sometimes that does involve going over high cost terrain to get to the low cost terrain. It depends on what weights you put on the different terrains. And in fact, the weightings can make a big difference. If you say I really don't like you walk over grass, then the robot will take a very long path to avoid stay on concrete and avoid walking over grass. If you say, well, I prefer concrete, but grass is a little less preferred, and you give weights like 0.5 and 0.4, then it might plan to go over a short patch of grass to get to the concrete to save going a much longer distance. So we didn't change any of the existing methods for that. How you go from a cost map to the optimal plan based on the weights that are given to the various patches, and in the paper it explains exactly the methods that we used. The innovation for us was just how do we generate that cost map. But yes, so it will absolutely under certain conditions will move over unpreferred terrain to get to the preferred terrain, especially if it'll save a long distance or if there's no other way to go.
Okay, perfect. Thank you so much.
Thank you. Thanks for the question.
Yeah, thank you, Peter, for this fantastic talk again and sharing your insights. And thank you, everyone, for the engagement. So I hope to see all of you in our next seminar. Have a great weekend.
Thanks all for being here.
Thanks, Peter.
Thank you.
Thank you.
Bye.
Bye.